Welcome to another episode of Math Problem Solving. My name is Bharat Divyang. Let's get started. So this is a problem that was posted in DMAT. So you have the powers of 3 being expressed as the sum of consecutive numbers. So 3 square, which is 9, is 2 plus 3 plus 4. And 3 power 4, which is 81, is basically 5 all the way to 13. The question says, what is the longest sequence of consecutive integers that add up to 3 to the power 10? My goal here is not just to solve this problem, but rather to help you build an intuition for problems of this nature. So let's get started. So first thing I'm going to do is to redefine the problem statement, which is what is the longest sequence of continuous integers that add up not to 3 to the power 10 but 3 to the power 5. Why is that? First, let's solve for something smaller, build the intuition around the problem, and then maybe extend it to 3 to the power 10 if it's possible. And in this particular problem, 3 to the power 10 actually is a rather large number that, it's quite possible that we might get sidetracked trying to deal with numbers of that large values. Okay. So let's take one of them, one of the values given here, which is 3 to the power 3, which is 27. And we know 27 to be the sum from 2 all the way till 7, right? So because 2 plus 3 plus 4 is 9, 5 plus 6 is 11, 9 plus 11 is 20, 20 plus 7 is 27. Now, if you look at it, there is of course a pattern. It starts with 2 and it keeps increasing by 1 and you add all of it. So I'm going to give you an intuitive way of looking at this value. First, I'm going to just list down the count of these numbers, right? It's basically 6 numbers put together. So the count goes from 1 to 6. The numbers themselves are going to be something that I'm going to list down, saying 2 is the first number and 7 is the 6th number. But I'm going to break these numbers in a different way. So I know that each and every number has something similar, which is they all have 2 as a part of them. So to me, that's the constant. And I'm also going to change some value that's going to be called as the variable. So 2 is 2 plus 0, 3 is 2 plus 1, 4 is 2 plus 2, 5 is 2 plus 3, 6 is 2 plus 4, and 7 is 2 plus 5. In other words, I have taken the value 2 to be the absolute constant, which is present in each one of these 6 numbers, and then written down the variable value as well. Why am I doing this? Let's take the next sequence, 3 to the power 4, which is 81, which the problem has already mentioned that it's from 5 all the way till 13. In this case, we have a count of 9 numbers. Starting from 5 going to 13, I'm going to do the same exact thing that I did for the previous one, which is the first value is 1, the constant is 5, variable is 0. The second value is 6, 5 plus 1, 7, 5 plus 2, 5 plus 3, 5 plus 4, 5 plus 5, 5 plus 6, 5 plus 7, and eventually 13 is 5 plus 8. Now, why would I do something like this? This is where our fundamental principle of fluid intelligence, which is similarities between differences and differences between similarities, should come in handy. So let's look at both these things. In the first case, we had 6 numbers going from 2 all the way till 7. In the second case, we had 9 numbers going from 5 all the way till 8. While they look to be very, very different numbers, there's now a pattern. I have a constant value. The constant value in each one of them is different. In the first one, it's 2. In the second one, it's 5. But nevertheless, they're all constant. The second one, the variable value, goes all the way from 0 till 5. 0, 1, 2, 3, 4, 5. And here also it goes 0, 1, 2, 3, 4, 5. But it extends all the way till 8. So now you can actually see the similarity. That no matter what that sequence is, if I have a sequence of continuous numbers, I can divide it as a constant value and a variable value that always starts from 0 and keeps going up until the count. So in other words, when I'm going to find the value for 3 to the power 5, I need to find the starting number. That's the start, because that's definitely going to be different. It could be different. And I also need to find out what is that count. So in case of 3 to the power 3, the count was 6, and 3 to the power 4, the count was 9. What is it going to be for the next one? So in other words, I have a constant layer where if I add all of them, it's nothing but the starting value, that's 2 times the count. So start times count is going to give me the sum of the numbers in the constant layer. For the variable layer, I just need to sum all the numbers from 1 till count minus 1. So in case of 3 to the power 4, I need to count it from 1 to 8 because there are 9 numbers. In case of 3 to the power 3, I need to go from 1 till 5 because there are 6 numbers. And the formula for these numbers, which are called triangular numbers, when you sum them up, is nothing but count minus 1 times count divided by 2. So now I can basically list down all these values. So when the power is 3, the constant is 2 to the power 6, and the variable is 5, which is 1 less than the count, times the count, which is 6 divided by 2, which is 15. So it's 12 plus 15, 27. It makes sense. For 4, it's 5 times 9, which is the constant value, that's start times count. And the variable is 8 times 9 divided by 2, which is 36. So 45 plus 36 is 81. The question now is asking you, what is that constant value when you look at 3 to the power 5? And what is the variable value when you look at 3 to the power 5? That's what we're trying to solve. So now let's list down all the values that we know so far, which is the powers of 3 from 0 all the way to 5. So the value, of course, 3 to the power 0 is 1, 3 to the power 1 is 3, 3 squared is 9, 3 cubed is 27, 3 power 4 is 81, 3 power 5 is 243. We know this much. The starting value for the first 4 of them, we already know. It's 1 for 0 and 1, 2 for 2 and 3, 5 for 4. We don't know what it is for 3 to the power 5. The count we know is just 1 for 3 to the power 0. It's 2 for 3 to the power 1 because it's 1 plus 2. It's 3 for 2 because it's 2, 3, 4. It's 6 for 3. It's 9 for 4, which you already saw. We need to find out what's the count when we deal with 3 to the power 5. The constant formula is going to be start times count. So I'm just going to multiply the 2 rows ahead of me and get all the values that I need. The variable formula is going to be n minus 1, as in count minus 1 times count divided by 2, which gives me these values. You can verify it and ensure that you understood it for each use case. So the constant value in this is 1, 2, 6, 12, 45. I don't know what's it for 5. The variable value is 0, 1, 3, 15, 36, and I don't know what it's for 5. So now you can see that there is a pattern, and we're looking at it in terms of the pattern. So let's take the case of 3 to the power 4, which is 81, and we divided this as a constant value and the variable. The constant was 45, the variable was 36. 45 was nothing but 5 times 9, and the constant was nothing but 8 times 9 divided by 2. In other words, the start times the count plus count minus 1 times count by 2. That's the formula that allows us to get to 81. So I know that the common value between both of these additive terms is the count. So I'm just going to take the count out, and I'm left with start plus count minus 1 divided by 2. I would like to ensure that the 2 is completely out, so I have only multiplicative factors. So count times 2 times start plus count minus 1 divided by 2 is going to be 81. So instead of writing count and start each time, I'm going to call count C and start as S. So now you can basically look at this whole thing as count times 2s plus, so C times 2s plus C minus 1 divided by 2 is 81. Or in other words, 2 times 81 is going to be C times 2s plus C minus 1. Now why I'm doing this is because C as well as 2s plus C minus 1 need to be integers, which means I can expand these factors as 2 times 3 times 3 times 3 times 3 is equal to C times 2s plus C minus 1. So in other words, I can combine factors on the left and try and equate it on the right, and that should give me a way to figure out what the count is. So So let's take the case of 81 because we know the answer here, and let's see how we could have arrived at the answer. So we have the use case, we have the value of c, 2s plus c minus 1. What is the value of s depending on that? And what are the values of the numbers, right? These are the things I'm interested in. So the first use case is where c is 2, which means the other factor needs to be 3 to the power 4, which is 81. And therefore, if 2s plus c minus 1, where c is equal to 2, is going to be 81, then I know that s has to be 40. So I can calculate the two values to be 40 plus 41, giving me 81. Okay, so this is how I would derive the values. The second one, I'm going to say c is 3, and therefore the other term there has to be 54. When I solve it for s, I know s is 26, and therefore the three values are going to be 26, 27, 28. And this is rather simple. The next one is where c is 6, because I'm going to take the first two factors, 2 times 3. What I'm left with is 3 cubed, which is 27. And therefore, solving for s, I'll know that s has to be 11. So 11, 12, 13, 14, 15, 16 is also going to give me 81. The next one is where c is 9, which is 3 times 3. And therefore, I'm left with the other one, which is 18. And in this case, s has to be 5. So s is 5 to 13, and this is the case that has been given as the example. This is the longest chain possible. Now it's also possible that count could be 18 and 2s plus c minus 1 is 9. In this case, s is actually minus 4, and you'll realize that it's minus 4 to plus 4 followed by 5 to 13. This would give you a chain of 18 because the minus 4 to plus 4 cancels out completely, and what you're left with is still 5 to 13, which nothing but adds up to 81. Now, the problem doesn't explicitly say that it's only long chains of positive integers. It just says integers, in which case we should consider the negative ones as well. So let's continue with this. C could be 27, 2s plus c minus 1, in that case would be 6. In which case s is minus 10, and therefore the value would be minus 10 to plus 10 and 11 to 16. I could also have 54 and 3, in which case it's minus 25, so it's minus 25 to plus 25 followed by 26, 27, 28. And finally, I could have count to be 81, 2s plus c minus 1 would be 2, in which case my starting number is minus 31, so minus 39 to plus 39 followed by 40 and 41, which would be the longest chain if it were integers. And if it's only positive numbers, which is what the problem seems to ask, it would basically be from 5 to 13. So let's go back to the problem. It clearly says it's only positive, it's 5 to 13, but we'll solve it for both. And we now are going to be looking at 3 to the power 5. So let's get started with the same thing. So I have the exact same values. So I can start with c being 2, which means the other factor has to be 243. Solving this gives me s is equal to 121. And as you can imagine, I have a count of two numbers, 121 plus 122 has to be 243. Similarly, if c is 3, then the remaining values have to be 162, in which case s is 80, and now you can see that it's nothing but 80, 81, 82, also giving me 243. The next one would be 6. The other factor would be 81. Solving for s would give me 38, and 38 to 43 will also add up to 243. The next value is 9. So I'm just combining 3 3's together, and what I'm left with is 233, which is nothing but 2 3, so I'm left with 2 times 3 cubed, which is 54, in which case s has to be 23, so it's 23 to 31. And finally I have 18, in which case I have the other factor to be 27, and s here has to be 5, therefore the value should be 5 to 22. This is where the positive values stop, because after this you will see that the count increases and the other factor decreases. So we'll just do it for 1, and as you can imagine, it's minus 4 to plus 4 followed by 5 to 22. So what we're going to do is, we're not going to go through all the cases like the way we did last time, but I'm just going to go to the extreme one, which was going to be 243 chain, where the other factor is 2 and the starting point is going to be minus 120, in which case this chain is going to be minus 120 to plus 120 followed by 121 and 122. So if the problem were to ask integers in general, I would say use case number 8 would be the solution. But if it specifically says only positive integers, which is what it seems to be mentioning, then it's use case 5. 5 to 22 is the answer. So now kind of let's go and solve our problem from the beginning. So we knew all of this. This is what the problem, it's stated, right? It's already given for the powers of 0 till 4. Now let's come to power of 5. So 243 is the value. The starting value is 5. The count is 18. So the constant is 5 times 18. The variable formula is going to be 17 times 18 divided by 2. In other words, constant value is 90. The other one is 153. Adding that together, I get 243. So what's the next step? The next step would be for you to take this and extend it to 3 to the power 10, which is going to be way more complicated in terms of the sheer size of the numbers. But the method is not going to be any different. Just putting this table, probably using an Excel to actually do this, can help you solve the problem and find it out for 3 to the power 10. If you do solve it, please share your answer in the comment section, and let's hope that this gives you the insight, or it's given you the intuition for you to solve a problem of 3 to the power 10, or for that matter, pretty much any power of 3. Thank you so much. I hope you found this video useful. If so, please do leave your comments, share this video, click on the bell icon so that you don't miss out on the next one. Thank you so much. I'll see you in the next video.